Hi everyone, this is Adnan Ali. Our team members are Hisu Park, Abdul Haq Belaidi, Ibrahim Isa, and Fadwa Al Maluhi. Today I'm going to present recovery of the cubic structure in mixed cation perovskite thin films by machine learning assistants. Perovskites they are extensively used in solar cell as absorption layer, and they are giving very promising efficiencies. It has the flexibility to mix different cations to bring stability to a structure and to tune its band gap. Also, it can be processed by solution processing method like drop casting, spin coating, inkjet printing, compared to other conventional vacuum-based deposition techniques. It carries the structure ABX3. A is alkali or organic cation, B is divalent metal cation, X is halide anion. By mixing different cations, we can bring stability to a structure, eventually to a device. We can tune its band gap, which is important for the photovoltaics and also in LEDs and other devices. When we add cations into a structure, we induce local disorder, and also it changes the lattice parameter, which eventually also changes the band gap. The next two slides will be presented by my colleague Hisu Park, which is about the computational part of this work. So over to Dr. Hisu Park.
Hello, my name is His Park. I'll discuss our machine learning approach in the next two slides. Goldschmidt's tolerance factor is often used as an empirical indicator to see perovskite cubic phase stability and deformation. This way is simple. We can find the appropriate A, B, and X elements to form a cubic perovskite only by using their ionic radii. However, this method lacks the details at each site. To provide a more sophisticated prediction, we carried out theoretical investigation varying the chemical composition. Using DFT methods, we have calculated the properties of pure perovskite, and using this result, we could look into the energetic and structural variation trend. Looking into these properties, we built a machine learning predictor to provide the energy difference between the cubic and ground state structure. This approach is well along with the same idea as Goldschmidt's tolerance factor is, only the aspect moves from structural fit to energy. Therefore, this enables us to predict the more subtle variation in a cubic phase transition. So this work aims to validate the ML model's prediction while we synthesize perovskite thin film, and we identify the gap between the prediction and lab scale demonstration. According to the ML guided diagrams, we chose to focus on the cubic phase stability of triple mixed cation perovskites. These three cations are cesium, methylammonium, and dimethylammonium. When we start from Goldschmidt's tolerance factor, for example, as shown in the left figures, one may notice that single cation compositions such as cesium and Ma give us tolerance factor below 1, indicating competition between cubic and tetrahedral structures by mixing the cations. In the meantime, as shown in the right figure, our ML model displays the predicted energy difference, and this value is denoted as delta HC by the color mapping. This indicates the composition dependent stability of structure relative to its cubic structure counterpart. Interestingly, the ML's phase stability diagram shows that we can expect a better cubic phase stability due to Ma and cesium intermediate concentrations.
Um, this work is inspired from the computational work. We mix double double cations, which is methyl ammonium and dimethyl ammonium. We added them in different ratios to get the cubic structure, which is the more stable one. We noticed that from the XRD, we noticed that up to 2% DMA incorporation, we can keep the cubic perovskite structure. But beyond that, the structure is no more cubic and it started starting. We can notice it from the peaks, the uh, opening up the peaks, broadening up the peaks, and also some of the peaks they just start disappearing. So the broadening of the peaks, it's an indication that there is stress and strain in the structure. So to have more dimethyl ammonium, what we did, we the smaller cation, which is cesium, into the double cation perovskite. We re- we prepare the solution and deposit thin film using the spin coating techniques. We notice that up to 10% of the cesium cation structure is a cubic structure, which is the most stable one. But beyond that, we notice that there is segregation of the lead iodide, and also there is a distortion in the structure. There are, we investigated it up to almost 76.5 moles of cesium. We noticed that at that concentration there are needle-like structures, and also it's from the XRD result we can see that it's not a cubic structure anymore. So from the initial tetragonal MAPI structure, methyl ammonium iodide structure, we notice that up to 10% it's a cubic, which is the most stable. We zoom um, on the signature peak, which is around 14.2, and we saw that peaks corresponding to 2, 5, and 10%, they are in cubic. They are at cubic of, degree of the 2 theta, but beyond that, the structure is non-perovskite, and there is no stability of the structure because there are more strain. We can also see from the ACM images of the corresponding concentration of the cesium into a double cation structure. Also, we linked it to the despacing. We can notice it that which despacing is cubic, which is non-cubic perovskite. So from the XRD result, we analyze that this concentration up to 10%, 10%, 15%, and the 75%. Up to this, these are the optimum concentration of the triple cation perovskite, which giving us the cubic structure. Also, we analyze it. Sorry. Also, we analyze the other, which is around 28.2 and 28.4. We noticed that the same trend was observed as it was observed for the 14.2 of 2 theta of the XRD. And also we plotted the spacing at that degree of 2 theta against the cesium content, and we notice the same trends as I mentioned. Also, we link it to the full width hub maximum and the crystalline sizes of the structure. So we did different analysis to find the optimum um concentration of each cation to give us the stable cubic perovskite structure. So um, this we I would say that this computational and investigation and model it's minimize the number of experiments we did, and it's really helpful to take guidance from the machine learning and minimize the effort to reach to an optimum concentration for getting the stable structure and to use it in the devices. Um, I will move to the conclusion. We are concluding that double cation perovskite it's suffering from severe instability, and to get the cubic crystal structure, we added the smaller cesium cation at S site in the perovskite structure. And we would say that this route towards the formation of cubic perovskite, it was accelerated significantly by the machine learning perovskite structure stability predictor. I would also conclude that this machine learning model is guiding us to a cost-effective and reasonable time-consuming lab synthesis effort to get the stable cubic perovskite structure. So this is what we conclude here. Thank you so much, and we are with the Qatar National Research Funding because this work it was carried out under the National Priority Research Program in PRP 8 and in PRP 12S, and we are also thankful to the Qatar Environment and Energy Research Institute for providing us all the facilities, and to the core labs of the CARI for the XRD and SEAM analysis, and for the computational. We are thankful to Texas A&M University at Qatar. I would like to mention this work is published in Chemistry of Materials, and our schematic representation it's accepted as the cover page. Thank you so much, and we are open to the questions.